As we've talked about, our two earlier definitions, we had Arrhenius, who just believed that free protons and free hydroxide made acid and base solutions, so therefore acids and bases that had them, acids that had the H's were acids, and of course the chemicals that had the hydroxide ions were also bases. And Bronston and Lowry expanded that definition to talk about the donating and accepting of protons. Now, if we're going to look at this definition right here of the accepting and donating of protons, what we have is we have hydrochloric acid donating a proton to the water. The water is accepting that proton, is acting as a base. Now, water, because it's gaining a proton, becomes H3O plus. And that H3O plus, okay, if you look at it closely, is due to water with its two lone pairs donating a pair to a free proton. So a proton with no electrons can, as we talked about before, coordinate covalent bond with this pair of electrons, right? This lone pair donates all of it to the bond, and then once it bonds, it's a regular covalent bond. But because we're adding a proton with no electrons, this whole thing becomes a polyatomic ion called a hydronium ion. And we've talked about this before. The hydronium ion with H plus is synonymous with acidic solutions. Now, I will say this. The H3O plus was born out of the Bronston-Lowry definition. Arrhenius, in its very basic limited scope definition, a small circle, probably did not consider the H3O plus because he talked about free, okay, protons and free hydroxides. But what I'm after here is talking about conjugate acid-base pairs. The word conjugate, okay, means same chemical plus or minus a proton. Let me tell you what I'm talking about here. Let me show you what I'm talking about here. So HCl gives off a proton, and what's left over, okay, is its conjugate base. So this is the conjugate base, okay, and this is the conjugate acid. These are conjugate acid-base pairs because they are the same chemical plus or minus an H. Now, in truth, because this is a strong acid, this is the very poor base. It doesn't do a good job of going in the reverse. But if it wants to go in reverse a little bit, let's pretend it does, what would happen is this would have to donate a proton because in the future, going left to right, chlorine has one more. So you can see that in the reverse, the chlorine ion, to go in the opposite direction, has to gain back that proton, which means it's what? Accepting a proton and acting as a base. It's an acid on one side, it's a base, and we call that a conjugate acid-base pair. The other conjugate pair is, well, you have a base on one side because it accepted, and now once it accepted, it is H3O plus. It's plus because it gained the proton. And this is a base on one side, and now it's an acid on the other, because if it was to go in reverse, this would give an H back. Now, it actually does not do this, and we don't have equilibrium for those purists out there, but I'm just teaching conjugate acid-base pairs. Let me write a more appropriate reaction, okay, in this, okay? And we're not going to talk about Lewis acids or bases in this lecture. I'm really trying to focus on conjugate acid-base pairs. But let's talk about ammonia. Ammonia, with its lone pair, has an ability, okay, to do what? Well, to ionize water, as you would say. It can actually yank a H away from the water. So it can actually, through a collision, bring an H plus from the water over. And if you see, this is acting as a base, and the water is acting as an acid. We don't think water acting as an acid because water by itself is a neutral pH because of its autoionization. Equal number of H pluses and hydroxides come off. But this relatively strong base can force its hand and yank the H away. We know why the H can do that because of this very polar bond. Now, what do we make? Well, we make NH4 plus. Because of this coordinate covalent bonding, we just now made the ammonium ion, H4 plus. I should put brackets around to show that it's a polyatomic ion. And of course, because the water lost a hydroxide, I'm sorry, an H+, now it is another polyatomic ion called a hydroxide. Now, let's clean this up a little bit. Let's write it in its preferred probably structure to see it. NH3 plus water makes the ammonium ion, NH4 plus, and the hydroxide. Notice that we're conserving not only mass here, but charge. A negative and a positive is 0 on this side. This is 0. But watch what happens. This is my base because water is forced to give up its proton to the NH3. And the water is acting as an acid because it's donating according to the Bronson-Lowry definition. And its conjugate pair, or its conjugate base, which means what's left over after it donates, is the hydroxide. So this is a base. If it's an acid on one side, in reverse, in this weak acid-base equilibrium, okay, it is a conjugate acid-base pair. Same chemical, plus or minus an H. After it donates a proton, it doesn't have any more to donate. An H plus won't come off an OH minus because it's now minus. But what can it do in reverse? Well, it could accept a proton from the ammonium ion going in reverse. We could say the ammonium ion is acting as an acid, and there is the other conjugate acid-base pair. Here is the base, and what's left over after it accepts is now an acid, and this is the other conjugate acid-base pair. You can see same chemical, plus or minus an H. If you look carefully, what we're going to get is the base, NH3, with its conjugate acid, NH4+. Notice the conjugate acid has one more proton than the base. And then we have what else? We have the conjugate acid, H2O, with its conjugate base. Notice it has, the base has what? One less H than the acid. The acid, my friends in chemistry, the conjugate acid, always has one more what? H, or proton. And the base, how low can you go? Okay, has one less. So if I was to ask you an arbitrary question like, hey, what is the conjugate base of, let's say, sulfuric acid? Sulfuric acid is listed in our table K here. Sulfuric acid is H2SO4. So what's the conjugate base? H2SO4 is the acid, and the base would have one less. HSO4, don't forget the negative. And I can ask this in the reverse. Now, why the negative? Because it lost an H+, right? When this acted as an acid and gave off an H somewhere, what was left over? And that's what a conjugate acid-base pair is. What's left over? Okay? So, very simply, if I asked the reverse, if I said, hey, what is the conjugate acid of HSO4 negative? You'd be looking for something that has what? One more H, because if it's a conjugate acid of this base, it should have one more H. So the conjugate acid of HSO4 is H2SO4. And these are pairs, same chemical, plus or minus an H. Let me ask you this question. If I have HCO3 negative, what is the conjugate acid? That means that this must be the base. What is the conjugate acid? And you would say H2CO3. It gained one more H+, right? To become an acid, it has to have one more. What is the conjugate? Okay, if I start here and say, what's the conjugate base of this? That means this must be the acid now. And the conjugate base of this should be CO3. Notice the conjugate base, -2, because it lost another H+. Notice the conjugate base has one less what? Proton than its conjugate acid. Notice when I had this pair, All right, the conjugate, forget Lewis, the conjugate base always has one less than the acid. Okay, and if you look back to here, the conjugate acid of this base is the ammonium ion. So one way to look at these is to look to see what happens in the future. So let's do one more, and then you can tell me if you get this. Okay, so let's take a weak acid, and let's take HCO3 negative. You guys come in, and let's take a weak something here. Let's go with let's go HI. This is going to make I negative, and H2CO3. And let's see if we can, even though this wouldn't be exactly equilibrium, but let's pretend it does. Let's figure out our acid-base pairs. This, well, HCO3 in the future becomes H2CO3. It has one more H in the future. Wait a minute. One more H would mean that this must have donated a proton, which means it accepted. So this is a base, and this must be its conjugate acid. If this is a base, because it accepted, this one donated, therefore it's an acid, and what's remaining on the other side is its conjugate base, right? So once I know one, I know the other. Here's the acid, what's remaining is the conjugate base. In the reverse, to go in the opposite, this has to donate to the HI to reform this. This accepts the base, it is. So all you got to do is find one, and what I do is I look in the future. I saw HCO3 negative in the future, it has one more. So that was it made me see that this one accepted, which had to be the base, this one had to donate. And if it's a base on one side, it's an acid on the other side. Okay? And hopefully that helps you.